My name is Monica Mendoza, and I'll be presenting my final project, which is on automatic language identification. The goal of my project is to build a neural network for language identification from an audio clip. Automated language identification is useful because it allows for the clip to be subsequently processed by an automatic speech recognition or translation system. As input, my model takes in an audio spectrogram and it outputs the predicted language: English, Spanish, Russian, or German. For my model architecture, I use a convolutional neural network to extract features from the spectrogram image, and my final layer is a fully connected layer with a softmax activation, which outputs the probability of each class. I use Keras with TensorFlow to build my network. During training, I use an NVIDIA Tesla P100 GPU. I'm running Python 3.6.5, and for my deep learning framework, I'm using Keras 2.2.4 on top of TensorFlow. I use the following Python libraries, which I've installed via pip: Librosa for audio processing and spectrogram generation, MoviePy, which is a video processing library, which I use for extracting audio from video clips, NumPy for array processing and storage, Pandas for processing data frames from CSV files, scikit-learn for obtaining the confusion matrix and classification results, and Matplotlib for plotting and visualization. The dataset I used was released by Google and is known as AV Speech, which stands for Large-Scale Audiovisual Speech. The dataset is available online and can be found in this URL shown here. The dataset consists of YouTube video clips, each featuring a single speaker with no background noise. One thing to note is that Google releases the YouTube ID of each clip, but does not provide the video itself. For this reason, it is up to the user to download the videos themselves. I do so using the command line programs YouTubeDL and FFmpeg. The original full dataset has over 4,700 hours of clips, with each clip being 3 to 10 seconds long, and there are over 50 languages represented within this full dataset. To simplify my problem, I only use a subset of the data. Specifically, I only take the first 3 seconds of each clip, which makes the length of input consistent across all samples that I add to my model. I take only 100,000 clips, which is equivalent to 83 hours, and I use clips only featuring the 4 most common languages in this dataset. Those are English, Spanish, German, and Russian. In this figure below, I show example frames from the AV Speech dataset. I wanted to show these frames just to give a representation of the diversity of videos within AV Speech. I go on to split the 100,000 clips into train, validation, and test sets using an 80, 10, and 10% split. I ensure that each set has an equal number of clips per language. One thing to note about the AV Speech dataset is that it does not provide the language of each video. I generate these reference labels myself using Google's language detection library known as LangDetect. I run the title of each video through LangDetect and save the language code. A couple of examples are shown in this snippet below. So for example, the first title is Neurolinguistic Programming for Sonic Communication, which Google detects as being English. The second title is detected as being in Russian. These serve as my true Y values, which I'll use in the model. After I've downloaded my YouTube videos, I can extract the audio from each video clip using the Python library MoviePy. I then generate spectrograms for each audio clip using the Python library Librosa. Spectrograms are a way to represent the frequencies seen in an audio over time. Specifically, I choose to generate spectrograms on the MEL scale. The MEL scale is designed to represent human perception of sound. Specifically, humans can better distinguish differences at low frequencies than at high frequencies, so the MEL scale better differentiates those low frequency sounds. An example spectrogram is shown in this image here. X presents time in seconds. The y-axis is hertz on the MEL scale, and the colors seen are decibels. If I process one audio clip, this results in a 94 by 128 sized array. 94 represents the frames in time, and this is based on the sampling rate of the audio and how I window the audio for the FFT. and 128 is the number of MEL bands I've chosen to represent the data with. These MEL spectrograms serve as the input X that I feed into my model. I'll now present an overview of my model architecture. As I've said, I've chosen to use a CNN to process the spectrogram as an image. In this code below, you'll see that I have three main convolutional layers, which have increasing filter sizes, 16, 32, and 64. These convolutional layers serve as feature extractors. Each convolutional layer is followed by a ReLU activation and a max pool. I then apply global average pooling. This summarizes the information from the spatial dimensions of the image, meaning the height and width, into one number. Thus, global average pooling outputs one number per depth dimension. Using global average pooling prevents me from needing to use a flattened layer. I then include a dense layer followed by a dropout layer with a dropout rate of 25%. I use dropout to prevent overfitting to the training set. My final layer is a dense layer with 4 units, with each unit representing one class. I use a softmax activation to output the probability of each class. Later, I can determine the most probable class and assign the audio clip that language label. I'll also provide details on how I compile and train the model. For optimization, I use the Atom Optimizer, which has been found to work better than traditional stochastic gradient descent. During training, I monitor the cross-entropy loss at the end of each epoch. Cross-entropy loss is used for multi-class classification problems such as this one. I also report the accuracy at the end of each epoch for both the training and validation sets. I use model checkpoints, saving the model at the end of the epoch if the model improves, meaning that the validation loss has decreased. I train my model using Keras function fit generator, which trains the model batch by batch using training and validation set generators. I use generators because the training data set of spectrograms is too large to store in memory all at once. In total, the spectrograms take up 9.7 gigabytes. I split up the spectrograms into smaller files of around 100 megabytes each, which makes the dataset easier to work with. The generators load in these smaller files one at a time, which prevents out-of-memory errors. Lastly, I use a batch size of 32 and train a model for 125 epochs. During training, I record the cross-entropy loss and the accuracy at the end of each epoch for both the training and the validation sets. Here, I present the plots of these metrics. The first plot here on the left shows cross-entropy loss for the training set, which is in blue, and the dev set, which is in orange. The dev set is another way to refer to the validation set. I have a vertical gray dashed line at the best epoch, which I've found to be epoch number 38, and I define the best epoch to be the one with the lowest validation cross-entropy loss. Here we can see at epoch number 38, the cross-entropy loss for the dev set is a little bit above 1. On the right-hand side, we have a plot of accuracy over epochs. Again, the gray dashed line represents the best epoch, matching the same best epoch as found in cross-entropy loss. The validation at epoch 38 is around 61.7%, and the training accuracy at that epoch is 62.7%. You'll see that after epoch number 38, the validation accuracy seems to level out. It doesn't seem to have an upward or downward trend of improving or worsening. However, the training accuracy continues to improve as I train the model for further epochs. I would expect to see that if I train the model for even more epochs, say for example 200 epochs, that the training accuracy would continue to improve, but not because the model is learning any features that generalize well, but rather because the model is beginning to overfit to the training set. Once I determine my best epoch from training, I use a checkpointed model to predict the language labels on the test set. I find that the test set accuracy overall across all samples and languages is around 57.31%. This accuracy provides the best estimate of generalization accuracy, which means the accuracy on samples not seen within the current dataset. Here I've presented a confusion matrix that shows the predicted versus true labels for each of our 4 classes. So we have DE German, EN English, ES Spanish, and RU Russian. The confusion matrix shows the true language on the y-axis and the predicted language on the x-axis. We can find that the predictions are best for English. Nearly all of the English audio clips are predicted to be as such. The model also performs well for Russian audio clips. There's around a 77% accuracy for those, but the model does not perform well for German or Spanish clips. There's a 30% accuracy for those languages. Notably, a lot of the German and Spanish clips are misclassified as being in English. It is interesting to think that different languages have different accuracy values. It is perhaps that Russian is one of the most distinct languages in the set. Perhaps there is overlap between German and English, and then Spanish and English. I do note that while performance is not perfect, this is a considerable improvement over baseline accuracy of 25%. This 25% is equivalent to randomly guessing 1 out of the 4 classes. In conclusion, I found that my CNN was able to generate better than baseline predictions of the spoken language from the provided audio clips. However, I believe that this model can still be improved to achieve better accuracy. With additional time, I would like to conduct these further investigations in order to improve the model. I can try better tuning hyperparameters for the current model or changing the types and sizes of the layers. For example, I find that my model might be kind of small right now, so I would like to increase the filter sizes in order to increase the capacity of my model to learn important features. I can also try other neural network architectures. One type of model that is particularly prevalent for this type of analysis are hybrid CNNs and RNNs, in which RNN layers are added after the convolutional outputs. RNNs make sense for this type of data because RNNs can model the sequential patterns within an audio clip. Specifically, I've seen a couple papers that show that CNNs combined with LSTMs perform well. I also want to try using one-dimensional CNNs. One-dimensional CNNs are sometimes appropriate for sequential data, such as these audio clips that unfold over time. I can also try to alter my sound representations, for example, changing my parameters used with the Mel spectrograms, or using non-Mel spectrograms, meaning spectrograms on the log or linear scale. I would also like to add more training data. This will help my model generalize well and prevent my model from overfitting. And I'd also like to try adding different foreign language classes. For example, I believe that Arabic and Chinese might have distinct sounds that will make them easy to classify from these other languages. Overall, I would love to explore these investigations for further work.